Thank you for coming for part 4 of our lecture. Dr. Emanuel, lecture number 24. This is part number 4 of the divergence and curl. Now, we just finished this example, and I just wanted to make mention of a few things. We have x in the I component. We have a y and a j, okay, centered around the j-axis, centered around the I-axis. So, and these are all, there's no circulation. We see that these are all 0. Okay, so they're going straight out. So that's where the source is leading. Now, we're going to change these values. We're going to flip x and y, and then we're going to make this a negative. So we're going to change it, and we're going to see changes. I just wanted you to see the difference. Now that we go to this one, you might not have remembered, but here it is, a minus y. That's what I said. So it's a different component that's on the x-axis, on the y-axis, on the x-axis, and on the y-axis. So we're still going to use this formula, dot product. This time, when we use it, we're familiar with this. This is the function we have used before. Now what we have is, we want to see if there is, this is only an x and a y component. So z's, it doesn't affect z, so f of z goes out, and there is no z. Okay, so these go out. So this goes to f of z, there is no f of z, and there is no partial with respect to z. So the only two that are left are these two. So we have the partial of f of y, okay, in respect to x, f of y here, respect to x, we take it and it's going to give us a 1. Then we're going to subtract it, and we're going to look at the what? The f of x, which is a negative y, and take it in respect to y, and we're going to get a negative 1. Negative times negative is a positive, which gives us 2 in the k direction. Now we're going to use this again, okay? We're going to continue, and we're going to use it in our next part of this example. So notice here, this time, because it is not 0, it circulates around the what? Around the z-axis. So it can help you to see where things are coming from and where they're going. Okay, so now we're going to continue this. For this vector that we just solved, calculate the following surface integral over a surface of S, which is a hemisphere of a radius of 1, centered at the origin. This is our formula. Our curl, then times the normality, the normal function, and then our surface area. So, as we can see, we need to find, and we already found that. We already found the curl of f, okay? Then we have to find the normal, okay? The normal vector, which we'll call n, and the surface area. So we see that the curl is 2k. Formula for the sphere with a radius of 1 is x squared plus y squared plus z squared equals r squared, which equals 1. Square root of 1 is 1. Okay, so now we also have our radius. So now we're trying to calculate the gradient of this angle here, of this equation that we have here. And if we take the derivative, okay, we take this in respect to x, so that's 2xi, 2yj, and 2zk. And as you can see, this one is a what? This one is a circular one. Remember, we changed these values. Remember that. Okay, we found the curl and the what? And the gradient. Now we need to find the normal unit. Okay, so we have our vector n and our ds. Again, this is our curl. This is our gradient. And so to find the normality, the normal unit vector for this specific function of our gradient, we have to divide by what? By its absolute value. So that's just our squares of the 2's. Then we have our, we pull out the 2 and we just have our x. Original formula for a what? For a circle. Okay, x squared plus y squared plus z squared. That's all of r squared. We know r is already equal to 1, so that's 1. So now the square root of 2 times square root of 1, which is equal to 2. So now we have our normal unit vector for our gradient. And all we're doing is dividing this by 2. That's all we're doing. So if we divide this by 2, then they all canceled, and all we have is xi, y, j, zk. Remember, we saw this originally. This was one of our first functions that we worked with. Okay. So if we multiply all of this out, we are taking down this specific curl dot the normal, our normal vector. We get 2k times our normal vector, and we wind up with 2z. Okay. So the surface is spherical or hemisphere, so there's spherical coordinates we have to use to find the volume. Okay, so where we have r is equal to a, which is equal to what? 1. Okay. Okay, we found the curl, we found the gradient, we found the normalization times the gradient, the gradient normal vector. We did that times, so now we only need to use our ds, find out what our ds is. What's the surface? Okay, so if we have a sphere or hemisphere, so the spherical coordinates we must use. So we have r equals a, which equals 1. We have theta goes from 0 to pi over 2, and we have phi, which goes from 0 to 2 pi. Okay, and we also have z is equal to r times the cosine of theta. The cosine theta is 1, so it's the cosine of theta. So ds is equal to r squared sine of theta, d theta, d phi equals 2a squared times the sine of theta d phi, which equals the sine, since a is 1, that just gives us the sine of theta d phi. Okay, so the next thing that we have here is that we're going to take this specific function, we're going to multiply it. We're going to take the dot product, as we saw. We already have the dot product, so all we're doing now is this result of our curl, our gradient, all of this just applying this times our surface area. Okay, so that's from 0 to 2 pi, 0 to pi over 2. And we have this 2z, because that's what we got from here, the gradient of the curl. So that's where the 2z comes from. And we already saw that this was sine theta d theta d phi. So we can take the 2 out, and we know that z is equal to what? The cosine of theta. So it's just left with the cosine of theta times the sine of theta d phi. Then what we have here is we have our 2 that comes out. We have our d phi as relates to this, which will give us just 2 phi. Okay. So, sorry about that. So what we have here is our sine times our cosine d theta. And so when we use d phi, is just going to be 2 pi because the 0 is going to go out. So it's 2 times 2 pi. Then we have the sine and the sine. And the goal of the sine is going to be sine squared over 1/2. And this will give us the cosine, will fit in nicely there. And we're taking it from 0 to pi over 2. So we take the sine squared at pi over 2 minus the sine squared at 0. It goes to 0. And so basically all we have left is our pi over 2. Okay, so we're going to come back because we're at 12 minutes already, and we will give a summary of our derivatives. Thank you.